So, hi again. Let's talk about base doping design. This is in the context of the current gain we just defined in the previous section. And it was a pretty simple expression, current gain. You want to increase the gain, meaning the amplification of your base current versus the collector current you can drive into the system. And this expression tells us that the gain can go up if you can reduce the base doping, okay? So if you reduce the base doping, your DC gain should go up. Now we can ask ourselves what's wrong with this recipe, and we'll touch on 3 items: current crowding, punch through, and base width modulation. So let's do that now. Now let's look at a more realistic device. Double diffused junction like this. The N+ region is very heavily doped, and then you have a base depicted here in green, and you have a lower doped collector, and we're looking at holes regulating the current flow through the double junction like that. Okay, so remember, you're injecting holes from the base into the emitter, and that controls a very heavy electron flow in the device, okay? You have electric fields that are in this junction, and if the doping is very small or in the base, you will have not perfect conduction. So you will have resistive losses in this green region. So the simple recipe says reduce NB to get beta up. But if you do that, you make the flow of the holes from the base into the collector more difficult. It becomes resistive. And what you really have is a resistance path along for the holes, and your potential is not constant. So you have a resistive drop. Remember, you have a quasi-Fermi level dropping. You have resistive losses. So you have an electrostatic potential throughout this green region that is not constant. All right, if that's the case, then you could say, well, I have an injection that is spatially dependent. So the injection here will be different than the injection here. Okay? And this is a forward biased junction. So the higher the potential, the more injection you get. So if the potential really drops down from large values here to smaller values here due to a resistive drop, that means you will have a lot of injection here at these edges. Okay? And you could write this down in an expression where you say, well, I now need to integrate my current flow, not just in my simple 1D model like this, but I need to do this, say, at the surface of the junction, along this line of the junction. Now, this would be a horrendous integral to do analytically. You can certainly transfer that into a computer program that will help you evaluate those effects. But the take-home message of writing down the expression here is that you now have a spatially dependent potential, VBE, base emitter potential. And that sits in an exponent. So small changes to that potential will have dramatic changes in both the base current and the collector current. All right? So having a resistive drop inside your base is not a good thing. And having corner effects is not a good thing. So, as I just stated, if you have an inhomogeneous electrostatic potential like this, you will have unequal, non-homogeneous current distributions, and that means you might have current crowding, and you might drive components of your current to a very high intensity versus other areas have low intensity. So you will operate the device in different regimes, so to speak, high current versus medium current regimes. You will have temperature gradients, all kinds of things could break loose in this kind of configuration. All right, so if that's the case, you will have resistive losses. There is a discussion of that in the textbook. So just reducing the doping in the base would increase the resistive drops in the base region, and that means higher resistance. You can discuss this with equivalent circuit elements that you attach to the intrinsic device. All of that is kind of not very nice for the device. Let's put it this way. All right. So if you have these non-uniform currents, they are not just inefficient, they can cause burnout. And one way that is technically really relevant is you have an interdigitated design where you don't, or you have large components of the device where you enforce a pretty homogeneous electrostatic field throughout the device, and you deal with a doping in the base that is not too small, such that you don't have significant resistive drops along this direction. But at least in these directions, you should have reasonably homogeneous electrostatic fields. So that's the concept here of an interdigitated design. So let me summarize here that this is a two-dimensional effect. It gets enhanced, and the effects are getting enhanced if you reduce the doping in the base too much. You could say, well, I'm going to increase the doping to reduce the effects of this current crowding and the resistive effects. But if you do that, so you increase the doping here, that means your current gain goes down. So that's not very good either. So you need to find a good middle ground on your design. And there's a couple of options to pursue. We'll go over that. And as I mentioned, the practical designs have this interdigitated architecture and layout. All right, so here's one element that we've now considered what would go wrong if you make the doping density too small. So in the next subsegment, we'll look at the effect of punch-through. So let's talk about punch-through here in a junction like this. All right, when we discussed PN junctions, we had looked at the modulation of the depletion regions. We had calculated that under bias, these depletion regions here, say, they vary under applied bias. So if you have a, remember I showed you how under reverse bias, the depletion regions could get very large, versus in forward bias, the depletion regions get smaller. So here, let's assume that this is the junction of the base to the collector, and I'm applying a larger reverse bias. That means I'm increasing this depletion region here and this depletion region here. So I'm encroaching the space, the physical space in the base. So while the metallurgical junction width might be WB, the electrical junction, as indicated here in W, is smaller than that. Okay? And in forward bias, I move this, if I deem this to be all zero bias, I can, I move this in forward bias, I make it slightly smaller. So this marches this way as a function of forward bias, but this marches in as a function of reverse bias, of cranking up the voltage on the collector side. All right, so here are the dependencies, right? So this width here, the base emitter length of the depletion region for the P side is as described here. It depends on the voltage. And we have VBE positive bias, so forward bias on this junction. On the other side here, where I had scribbled already, we have the other expression that depends on the base collector voltage. Okay, and that voltage is negative. We have that in reverse bias. Okay, so as we ramp up the base collector voltage, as we push more current through the device and collect the current on the collector, we have a growth in XP BC, which means a reduction of the electrical base width. All right, so number one, you're modulating this base width here. We'll talk about that in a second. But you can actually get to the point where this is starting to encroach quite a bit and basically vanishes. Okay? And if it vanishes, you've destroyed the junction. You have something called punch through. So if that's the case, your device is no longer working. So if your doping is too low in the base, so if that is too low in the base, you can say, let's say it's these guys were equal, NB and NC. Then if this gets too small here, then this pushes up XP, so it advances the rate at which you make the electrical junction smaller. Okay? So similar here, if you say, well, my emitter doping is larger than the base doping, so I can neglect this term here, but again, I'm stuck with 1 over NB. Again, as oh, this goes in the other way though, so never mind, I'm sorry. All right, so that's being said, punch through. Let's look at the next effect that can reap havoc if you dope too low, and that's called base width modulation. Again, I'm starting from these sketches here of a dependence on bias on this electrical base width. Okay, so the junction, the metallurgical junction width might be this big. But we know that we have a depletion region in those junctions on the left and the right. And the component here on the right, that's the base collector junction here, is infringing or creeping into the metallurgical junction. And I can calculate that value. That's here. That's this XP. Okay? Now, that means I'm modulating the base width. It's not the physical base width, but it's the electrical base width that goes into the current expressions that we had calculated. Okay? So if that's the case, I can substitute my base width like this with an expression that now contains the depletion region. So I'm going to consider here the electrical width of this base junction. And if you do that, you're starting to have on here a dependence on VBC, and on here a dependence on VBE. That's bad. That means your gain depends on the voltage you apply. Okay? It depends on the collector voltage. So that's not a good thing. So you like to avoid that. And we'll discuss some of this in the next slide. So ideally, as you increase your base collector voltage, eventually your current should saturate. Okay? You get all the current you can get, and you modulate the current here with a base current. Okay? But so let's assume you fix the base emitter voltage, so you're running on this line, which means now when you increase the VCE, you also increase VBC, And as you do that, you increase the depletion of the base collector junction. And if you do that, then you increase the total current IC. Because remember we had sketched current in the junction that goes down from the, here's the beginning of 0 WB. And if I make this smaller, I'm changing the slope here, and therefore I'm making the current bigger. Okay? So I increase this current, so what happens is the current actually gets larger and it hops onto a new line. So ideally it would be flat, but as I make the junction smaller, I change the slope of the electron density, delta N. I therefore increase the current. And then I get a slope here that is not what I want. This is not an ideal transistor because the output current changes as a function of the base collector voltage. Okay, so what you can do is now you can extend that slope where at your working area, let's say you have, this is your normal working voltage, you can extend that tangential back to negative voltages. And that distance between VA and V0 is called the early voltage. And it's not, it's in the, for the namesake of one of the early researchers, Early, who explained this effect well. And that is due to the base width modulation in your BJT. Okay, so that is not an ideal thing. Now, let's look at this a little bit in more detail. Okay, so I'm writing down IC dVBC. So this is this slope here, okay? All right, so that is IC over the VBC plus some VA. Okay, so I'm operating here at this particular VBC. Now, in an ideal world, you would want to have this guy here move to infinity, right? And for the argument's sake here, this slope is pretty much exaggerated, okay? So you can assume that VA better be much bigger than VBC, okay? So we're going to drop this dependence here. So we'll just call it IC over VA. Okay, just to make life a little simpler. All right. Now we're going to calculate VDC again, beta DC again. We're going to drop out the term NI, and we have the same expression as what we have up there. And we're going to write down the expressions, we write down the current again for the collector. Okay, again we have two components, the forward bias component VBE and the reverse bias component VBC. Both of those have the electrical base width in it now. Okay, so we're going to carry, we had these current expressions before, but now we're going to plug in the electrical base width. Okay, so let's carry this over and calculate again the slope here. All I'm doing here is, see, this is the same guy as this. So I'm just doing my usual trick. I'd like to differentiate against a slightly different quantity. So I'm doing a differential of my slope up here. And I introduce the product, which is the base doping charge and the electrical base width. Okay? And that is really the charge that is sitting in the base. Okay, so now let me carry this through. I'm after originally this guy here, so this guy is here and this guy is here, and I introduced this factor. Now, I can assume that the doping is constant, so I pull this out, and I end up with a differential with the base width, and I'm looking at the charge in the base as a differential change of the base collector voltage. Charge in the base as a differential of the base collector voltage. That should ring a bell to you. That's a capacitance. That's the base collector capacitance in the system. So we'll discover some of this in a second. So now I'm going back to my current that I had on the previous slide. Here's my forward bias current. Here's my electrical width I have. And here's the reverse bias. Let me, just for argument's sake, call this whole current expression as some function divided by WB, the electrical width. Okay? And I'd like to differentiate that term with respect to the electrical width. Well, if I do that with a chain rule as 1 over WB, or I get minus 1 over some psi over WB squared, I can substitute that back in, and it's minus IC over WB. Okay? So now I can substitute this guy back in here. And I just said that this is a capacitance, right? So now I have an expression for this slope here as a function of the electrical base width and the capacitance on the collector side. All right, so let me pull these together. I can equate these two, right? I can pull this guy and this guy. And yeah, that's what I did here. And I can solve this for VA, okay? So basically I equate these two, I solve this for VA, and I find what? An expression that now depends on the base doping, on the base width, electrical base width, and on the capacitance on the collector base. Okay. And in an ideal world, I would like this to be flat, right? So I'd like to have VA go to infinity. Okay? So that would be a cool thing to do. So what could you do? You could increase the base doping. So ramp this up. You can make the base longer as well and make this larger. Or maybe you could consider something about this capacitance here. And that's what we'll talk about in the next segment. And this capacitance is the collector base capacitance. All right. So we just talked about base width modulation with the early effect here, or early voltage. And so you reducing the base doping is making this this early voltage small and makes this transistor non-ideal. So what are we going to do next? We're going to look at collector doping, where we can manage some interesting aspects and maybe make the design better, but we'll discover some other detrimental effect as well, the Kirk effect and base push out. So I'll see you at the next section.